Okay.
Great. It's my pleasure to have José Gil-Férez tell us some very interesting things about Jónsson's lemma for partially ordered varieties.
Yes. Thank you. Thank you. It's a pleasure for me that you want to listen to this. So, yeah. So there is this very famous result by Jónsson called Jónsson's lemma, and on the other hand, there is a development of other kind of structures that are like algebras, but also they have incorporated an order, partially ordered algebras that was developed by Pigozzi. There is an article of 2004. And the idea is then to try and prove that this Jónsson's lemma is also valid for these other, not classes of algebras, but varieties of partially ordered algebras. So this is going to be my presentation. First, I'm going to speak about the relevance of Jónsson's lemma, why it is an important result. Then I'm going to show you not the original proof, but a proof by Jónsson. But Jónsson made this proof, and what is nice about this proof is that it distinguishes two parts, one that is more lattice theoretic and the other that is more algebraic. And then the lattice theoretic part is just the general setting that we will use later on to prove our result by imitating the algebraic part. But the lattice theoretic part is going to be true because it only depends on the structures of lattice. Then I'm going to show you a little bit how Pigozzi developed this universal theory for partially ordered algebras. And you will see that, you will recognize that all these theorems for the classical theory and more or less all of them are going to lead to these partially ordered classes of algebras. And finally, the shorter part is going to be actually the actual proof that this Jónsson's lemma also is valid for partially ordered varieties, because we are going to profit most of the works of Jónsson, but instead of applying it to the lattice of congruencies, we are to the corresponding objects of these partially ordered classes of algebras. So let's go then to the relevance of this theorem. Why is this Jónsson's lemma important? Well, this lemma, in order to understand this lemma, we need to know a few concepts. First, well, I know that many of you also probably know all these concepts, but for the sake of the ones who don't, I'm going to repeat. So a variety is a class of algebras that is determined by a set of equations. And usually when we have a class of algebras K, we denote by Vk the variety generated by this class of algebras. A typical example, if you have the Boolean algebra with two elements, you calculate all the algebras that satisfy the same equations as the Boolean algebra of two elements, and you have all Boolean algebras. So this will be the class of algebras generated by the two Boolean algebras. It's the variety of all Boolean algebras. An element, every element of a variety is a subdirect product of subdirectly reducible elements of B. And the meaning of these words is not so important right now. What is important about this result is that you could consider those elements of the variety that are called subdirectly reducibles as the fundamental parts from which every other element in the algebra can be constructed. So if you know the subdirectly reducibles, you have a complete description of your variety. That's why subdirectly reducibles is like having the prime numbers in order to understand what all numbers are. You know what the prime numbers are, you know how all the other numbers are built up. You know your subdirectly reducibles, you know how all the other elements of your algebra, of your variety are constructed as subdirect products of those.
So when is the tool the only subdirectly reducible, or
yes,
the other ones?
Exactly. Only the two elements in algebra is subdirectly reducible. Yes.
So you get a very nice.
Yeah. Yes. Now, usually we are going to write K sub Si to denote the subdirectly reducible elements of the class K. And what we have then is that every variety is generated by its subdirectly reducibles. Now, okay, so if you give me a class of algebras K, you generate a variety, and you look for the subdirectly reducibles, how do you find them? Where are they? Which kind of objects are they? So is there any technique to find them? And Jonsson's lemma is helping us to find all those subdirectly reducibles. You see, this process of generating the variety is made out of three fundamental operations. One is construct all possible products of elements of K. Then take all possible subalgebras of those, and then take all homomorphic images of those. So you have products and the subalgebras and the homomorphic images. Okay. Subalgebras and taking homomorphic images, those are processes that reduce your algebra, meaning reduce the size of your algebra somehow. So if you start with a finite algebra, the subalgebras are going to be of a smaller cardinality, and the homomorphic images are also going to be of a smaller cardinality. So these two processes, subalgebras and homomorphic images, are quite controlling. But the first operation that you have to do is construct all products, and products are going to enlarge the cardinality as much as you want, right? So in principle, it's very difficult to know where those what are going to be those subdirectly reducibles, because you have to construct all products and then subalgebras and homomorphic images of those. But what Jonsson's lemma says is that if your variety is nice enough, and nice enough in this context means your variety is congruence distributive, whatever this means, then your subdirectly reducibles are going to be homomorphic images of subalgebras of ultra product. And I know that ultra product sounds more stronger than product. It sounds like if you have an ultra product, it's going to be something even larger. But no, it's the opposite. Ultra products are quotients of products. So it's actually something quite small. And then it's a quotient that is like a big quotient. So much so that if you have a finite class of finite algebras, the ultra products are the algebras themselves. You don't have more algebras. So if you consider all the products of Boolean algebras with two elements, all the products are going to be, well,
oh, this answers my question about Boolean algebras.
Yes.
Right? Because I have only one generator, and
yes.
It's two, and I don't have to take products of two now.
No, exactly. Because
and so there's only one.
Exactly.
Which is the two.
Which is the two. And then the ultra products of the two is just the two. So
okay. Yeah.
So in combination, the Jonsson's lemma in combination with this result then makes finding the subdirectly reducibles easier. Because if you really have a finite class of finite algebras, then you only have to take subalgebras and homomorphic images, and your subdirectly reducibles are going to be among those, which are going to be finitely many. So it is an algorithm to find the subdirectly reducibles. Yeah.
So you convinced me that if I start with a finite class of finite algebras,
yes,
this is super powerful.
Yes.
And in logic, often that happens, right? So
yes.
I have only finitely many truth values.
Yes.
That makes a lot of sense.
Yes.
But like, suppose I have an infinite algebra. Is this still helpful or not so much?
Still, it's going to be helpful because it is going to. You have to work a little bit more because you have to find out what the ultra products are going to be of that finite infinite algebra. But it is always
it's still helpful.
A smaller class than it's not comparable because it's not class products, but it is still going to be much easier. The only catch is that you have to prove that your variety is congruence distributive.
Okay.
And congruence distributive means that the lattice of congruences of the elements of your variety, all of them are distributive lattices. This is what congruence distributive is. The lattices of congruences are distributive. Okay.
But you're saying you only have to look at the elements of K.
Yes.
Because you don't, when you start with K, you don't have the whole variety.
No. And that's the problem. Yeah, that's the problem. If you start with a class of congruence distributive elements, this doesn't mean that the variety is going to be congruence distributive. No. That's the.
Oh, the K is not the same as that K.
Yeah, no. If K is a finite class of finite algebras, then the ultra products of K is K. This is true, but.
No, yeah, but in your when you say K is congruence distributive,
yes,
you mean K the variety.
Yeah, the variety.
You don't mean the generators.
Yeah, exactly.
Okay.
Yeah.
Any class.
Any class is congruence distributed
Yeah,
if the
yeah.
elements of that class.
Yeah. So if I want to know whether V of K is congruence distributed, I cannot just look at K.
You cannot
It's
just
more
look at the
complicated.
general.
Okay.
I'm going to mention something at the end how to do that.
Okay.
Now let's look at Bajone's proof of this result. This is a paper of 1994, and as I was saying before, I like this proof because it looks longer than the original proof, but on the other hand, it clearly separates what is the part that depends on the lattice theoretic properties. So this congruence distributive, where the congruence distributive thing appears. Why is this relevant? So it is not what is important for the lattice part is the distributive. Where is that distributivity going to play a role? And the algebraic part, it is what you do with your algebra. So it has these two clearly distinguishable. Okay, so let's start by recalling some concepts. Yes.
So what is the kind of concept of this thing? I couldn't pronounce it, but his paper is about improve Jónsson's lemma,
Yes.
or he has different purpose.
No, the purpose of the paper is to prove Jónsson's lemma again using a different idea.
Like a different approach with different ideas.
Yes, it's a different approach. Yeah. His idea is to distinguish because he has other results about a concept that he called the compactness of a compact set in a lattice, and then which is not the same as a compact element of a lattice. And then he wants to show that this notion of being a compact set in a lattice can also be used for something else, and in particular to Jónsson's. That's the rest of this. So a lattice is complete if all the joins and all the means exist. An element is compact if every time that this element is, maybe I can make this a little bigger. Every time that the element is covered by the join of a set of elements of your lattice, then there is a finite subset that also covers the element C. It is the typical generalization or the typical abstraction of the notion of compactness from topology. We denote by K of L, the compact elements of L. And one nice property of compact elements is that it is a set that is closed under joints. So it is a joint set lattice. This is true because if you cover the join of two, then in particular, you're covering each one of them, and from each one of those, you can extract a finite subset, you put them together, and then you still have a finite subset. So if this forms a joint set lattice, we say that a lattice is algebraic if it is complete, and moreover, every element can be expressed as the join of the compact elements that are below. Every element is the join of the compact elements that are below. Hi, hello, come in. And now this is an idea that I have only seen in this paper, and I hope that the topology people can help me here and see if they have seen this before. If you take the compact elements of your lattice and you take the upper closure, this forms a basis for a topology. Have you seen this topology before? Because I haven't. And then we are going to be using this topology. We are going to, and Bajone claims that this is a topological lattice, meaning that the lattice operations are continuous with respect to this topology. I haven't checked it, and it is not used. So, but it is a quite interesting topology. It is a basis of a topology because the upper set of the join of two compact elements, which is going to be also compact elements, is precisely the intersection of the upper set. So this means that this set is closed under arbitrary, under finite intersection. So it is the basis of a topology. So you take that topology, the basic opens are going to be the upper sets of the compacts. So this is a compact lattice, and now he says, okay, a compact set of your lattice, not a compact element, but a compact set of that lattice is going to be a compact set according to that topology. So this is what a compact set of lattices is. It's a compact set with respect to the topology. So the notion is that what is it? Yeah, that for every set of opens of that topology, if S is covered by those open sets, then there exists a finite subset of those that also cover the set S. What this means, I mean, the translation of that into elements is complicated, but the notion is quite clear. It's just a compact set of a topology. Okay, so now, of course, in particular, if you have a finite set, this finite set is going to be compact always. So it's the topology. A couple of concepts more. One is mid prime. A mid prime is an element of your lattice that, if it sits above the join of some set, finite set, about the mid of some finite set, then it has to sit above some of the elements of the set. It's mid prime. It has the analogous will be the mid irreducible, that if X is the mid of some finite set, an empty finite set, then X has to be one of those elements. So the weakening of mid irreducible is mid prime, in which the equality is replaced with this. And if we are in a distributive lattice, and that's going to be the point of everything, is that if you're in a distributive lattice, mid irreducible and mid prime coincide. The elements that are mid irreducibles are exactly the elements that are mid prime. Okay, so I needed all these concepts, and now let's start with Bajone's proof, the lattice theoretic part. First of all, he has this very nice lemma that tells me, remember what a mid prime is? Mid prime is if your element sits above the mid of a finite set, then it sits above one of the elements. Well, what this lemma says is that if your lattice is algebraic, then if mid prime can be characterized in this way. If it sits above of the mid of a compact set, then it sits above one of the elements. So you see, it is replacing finite with compact. So actually, the proof from right to left is immediate because every compact is finite. The important is the proof from left to right.
Every finite is compact.
Sorry?
Every finite
is compact, yes, sorry. The other proof, if it is mid prime, then you have to prove that this is going to be also true for compact sets. I can show you the proofs. I wrote them. So if you are really interested in okay, let's see one of these proofs because I think at least one is informative. So how do we do it? Well, take an S, a non-empty compact set, such that the mid of that set is below X, with X being mid prime. Suppose that all the elements of S are not below X. Then we will get a contradiction from there. Since L is algebraic, every element is determined by the compact elements that are below. So this means that there is going to be some element here. So sorry, I am confused. So this shouldn't be S of I. So it is there for every element of S. There is going to be some compact element that is going to be below Y, but it's not below X, because otherwise all the compact elements below Y will be below X, and then Y will be below X. That's the thing that is happened. So we found one compact element that is not below X for every element of X. This means that all S are going to be covered by all these basic open sets. And in particular, because S is assumed to be compact, there is going to be a subset S0 of those S's, so that S is also covered by those finitely many open sets. And then, well, the mid of these would be smaller than the mid of the others, and the mid of smaller than the mid of X, and then there is one element of S0 such that Cy is below X, but that's impossible because all the Cy's were selected so that they are not below X.
Not sure why the meet of S0 finite set meeting to something below the whole set S. Is this the problem?
Yeah, I see. So it is. I see. S0 is a subset, so the mean is not going to be smaller.
Check later.
Yeah,
Something.
we can check later. Yeah, but yeah.
Varieties is like you took.
Yeah, I think
That would still be, yeah, that would still be like finitely many of these CYs, which
Yeah.
you know are not below X, right?
yes.
So you don't, yeah.
Well, yeah, we can. Yeah, we can check later. Yeah,
Yeah.
I'm sure that
I think
it's
a
correct.
picture
But
will do it. Just
yeah,
all you need is to
yeah.
that union of CI of up CI
Yeah.
Yeah, is the fact that S
contains
is
S.
covered by
So those are all lower bounds. Together they make lower bounds.
Yeah, the union of all the
Yeah.
meet of that entire
Oh,
union
yeah,
is
they are
smaller.
covering S, okay.
I
yeah.
see. Okay, good. So that's
Did you
Yeah,
confirm
yeah,
you used
yeah,
the right?
yeah, that's,
Yeah,
that's from there, okay,
Right, okay.
from there.
yeah. All right. Thanks.
Okay, so we changed now mid prime now is characterized as with compact sets, not only finite sets. That is going to be important. And now what do we suppose that you have a subset of your algebraic lattice and you have a compact element. I'm going to denote by C upper E, the upper set of C, but intersected with B. So what I'm doing really is I take subset B, and I'm going to restrict the topology to that set. So I just take the intersections of all the basic open sets with that. If you have an ultra filter over that set B, which just means a maximal filter of the powers of B, then we define IU to be all the compact elements so that this basic open set sits inside U. And now I take XU to be the join of all those. Now, my lemma 2 is going to tell me that if I did that, let me just then so let me show you still the definition. XU is the join of IU. So obviously, if you have a compact element that belongs to IU, then these compact elements will be smaller than XU because this is the join of them all. But this lemma says that the other side, the other direction also works. Every time that you have a compact element that is below U, then that compact element will belong to that set IU. The third lemma says that okay, now take any set, any subset of L, and consider all possible ultrafilters over B, and consider all the elements XU, each one of them for one of those ultrafilters. This process of taking all the elements XU for all the possible ultrafilters for all the ultrafilters of over B, this process is a closure operator. It is not the closure operator of the topology. It is simply a closure operator. So this means it is monotonous, it is going to be idempotent, and it is expansive, expanding as a closure. And finally, lemma 4 is that this B prime is always going to be a compact set of your topology. So what you are doing is taking, you have your algebraic lattice. Consider any subset. This is going to tell you how to construct a compact subset that is going to be above. and then it still is not going to be too much far away from your set. So this is what this is to. This is the. Okay, now you see all this is purely algebraic, and here I have written the proof of most of those things if you want to check later. But let me show you how then Bajone applies these lattice theoretic results to prove something, to prove Jonsson's lemma. First of all, he does this. He proves this lemma. If you have an algebra, and then, of course, the lattice of congruencies of your algebra is always complete, and every congruence is determined by the finite congruences below it, so it's determined by the algebraic. It is algebraic. All the congruences, actually, an algebraic lattice is one that is isomorphic to the congruences of some algebra. So, algebraic this is going to be an algebraic lattice. So the theorem, all the results above are going to apply. You take any set of congruences B, consider one ultra filter over those set of congruencies, and now you consider all the quotients by all the congruencies in B, and now take ultra products of those and subalgebras of those, and then close it under isomorphisms. Well, A quotient XU is going to be always one of those numbers. So let me say that slowly. If you have an algebra, a set of congruencies in an ultra filter over those congruencies, but Jonas tells you how to construct one element of this lattice. So but Jonas tells you how to construct one congruence so that when you make the quotient, this is going to be a subalgebra or isomorphic to a subalgebra of an ultra product of all the quotients of all by all the possible congruencies of B. So that how do we prove that? I think it's important to see this result. So consider your algebra A, your set B of congruencies, and now you make all the product of all the quotients. Now you have an ultra filter over B, so this means that you are going to have here the canonical projection of this product with respect to the corresponding congruence generated by it. Okay, the composition of those two would be a homomorphism F from A to this quotient of this product. Now, what is the kernel of this quotient? Well, a pair of elements belong to the kernel, if and only if when you apply this morphism and this other morphism, it gives you equal elements. So this means that when the equalizer of nun of A and nun of B is in the ultra field, that is how this quotient is defined. So the equalizer of the nun A and nun B belongs to the ultra field. This means that what is the equalizer? The equalizer is all the elements of B so that the projection of A is equal to the projection of B. And when is the projection of A, B is going to be equal to the projection of B? When the congruence generated by AB is included in the congruence eta. And this means that you are taking, you see, all the elements of B that are above the congruence generated by AB. So you are taking the congruence generated by AB, upper set, and then you intersect with B. But the congruence generated by one single pair, this is a compact element of the set of congruencies because it is finitely generated. So this means that actually you have a compact element so that the upper set intersected with B belongs to U. That is exactly the definition of the set IU. So you have that this congruence belongs to IU. But this congruence belongs to IU, then this means that the congruence is smaller than the congruence XU. Because XU was the congruence constructed so that this is true. XU is actually the join of all the elements here. And this, what means is that AB belongs to the congruence XU. So what we prove here is that the kernel of F is precisely that congruence XU that we drew before. So XU is indeed a it is by the isomorphism theorem. So here, this is going to be a subalgebra of this. So it is a subalgebra of an ultra product of all those things. So that's the proof. That's the lemma that we need, and then Jónsson's lemma says that if your variety is congruence distributive, then the subtheoretically reducibles will be in the HS ultra product. Okay. How do we prove it? We know that the variety generated by K is the class of algebras that is obtained as all the homomorphic images of all the subalgebras of all the products of elements of K. Okay. Let's start by considering an algebra that belongs to the SPK. So a subalgebra of a product of K. Later on, we are going to make the quotient. So we are separating these two parts, right? We have here the homomorphic images, and here it's the subalgebras of products. Let's start with subalgebras of products, and later on make a quotient. So it is a subalgebra of product of elements. Consider now B all the congruencies, so that when you take the quotient, this is indeed a subalgebra of an ultra product. It's only let's just take those congruencies, the ones, so that when you take the quotient, this is going to be isomorphic to a subalgebra of a product of elements. And now take an arbitrary ultra filter over that set B. Now, by the previous result, the quotient of A with respect to that congruence is going to be isomorphic to a subalgebra of an ultra product of this set. But what are those A quotient eta? Eta are congruencies so that the quotient is isomorphic to a, so it is in ISPUK. So this means that this here is a subclass of ISPUK. So you have that this is included in ISPU of ISPUK, which is equal to ISPUK. Because ISPU has this proof. So what we just proved here is that XU actually belongs to B. So every time that you have a B, so not every time that you have a, every time that you have, so you take your B, this set. You take any ultra filter over B, every single time XU belongs to B. So this means that B is closed under this process. So B is equal to B prime. But B prime was proven to be compact. So this is a compact set.
Prime is closure.
Yes, that's closure. And now, what happens? Now we are looking for the subtheoretically reducibles, right? Before we consider an algebra that is a subalgebra of product K. Now, suppose that you make a quotient and it turns out to be a subtheoretically reducible. So you're taking here really an arbitrary subtheoretically reducible element of your variety. Then the congruence is completely meter reducible. In particular, it is meter reducible. And because we are in a distributive lattice, this is the same as being mid prime. And we proved before that mid primes are not only characterized by finite set, but also by compact sets. So this means that if this is above a compact set, it has to be above some of the elements of that compact set. Well, the intersections of all the elements of B is the trivial. It is the trivial congruence. And this is always inside any other congruence. In particular, there should be some element of B that is below that congruence C. And this means that we can express this quotient, this divisible algebra, A quotient C, as the quotient first with eta, and then with the corresponding congruence eta quotient C. And this then belongs to, this is a homomorphic image of this algebra here that was by the choice of eta, which is inside this this set P, is an isomorphic to a algebra. So this is H ISPUK, so which is ISPUK. That's it. Okay. Wow, it's too late. Okay, so Pigozzi developed this theory of universal theory of partially ordered algebras. And would I think for the sake of time, I cannot explain you everything because I only have 20 minutes. But let me show you the highlights of this theory, because you're going to very quickly identify the main stepstones of classical universal algebra. What is the difference then between classical universal algebra and this ordered algebras? Well, first, when an algebraic type or signature is a set of symbols that we use to denote the fundamental operations of the algebra, together with a map that tells us to every signature what is the arity of the symbol. Okay. What we are going to consider now are going to be algebras in which the fundamental, so they're going to be algebras that are going to be also partially ordered, and the fundamental operations are going to be either monotonous or antitone with respect to each one of those in every coordinate. So what we need to do to define this concept is a set of operation symbols, and moreover we need a polarity. A polarity is just a map that tells me to every symbol it's going to give me a sequence of plus and minus, a finite sequence of plus and minus. And then to this pair set of symbols together with this polarity, we call it an order type. And the length, if you take the length of those, then you forget the information about which coordinate is positive, which coordinate is negative. You only know the number of coordinates. If you take the length, then this is a classical algebraic type. So a set of symbols together with the arity of MC. Okay, so just to fix ideas, imagine that you want to write in the language of Haydn algebras. The language of Haydn algebras, we have symbols to denote the meet, the join, the arrow, and constant 1 and 0. So now the polarity is going to tell me that both meet and join are positive in both coordinates. And this is going to be, when we define what a Haydn algebra is, this will correspond to the fact that meets are increasing in both coordinates, and joins are also increasing in both coordinates. But the arrow should be negative positive, meaning that the arrow is antitone in the first coordinate, but isotone in the second coordinate. Yes?
So categorically, this is like opposite variances, right? Going contra.
Yeah, yeah, exactly, yes. And the constants are going to be assigned the empty list. Okay, this is the idea. Now we have the language, And now we can define what a partially ordered algebra is using that language. First of all, we have the definition of preorder. Preorder is a relation that is reflexive and anti-symmetric. And moreover, if it is transitive, call it a partial order. We're used to those. Now, if you have an order type sigma, and you have a sigma algebra, so just forget about the varieties, just take the length of the symbols and create an algebra out of this language. And you consider a preorder of the set A. We say that this is a sigma preorder of A if indeed all the fundamental operations are isotone in the positive coordinates and antitone in the negative coordinates. So here is the definition. So this means that every time that you have, for every symbol and for every coordinate smaller than I should say smaller or equal than the length of the symbol, and every time that we have A1, AN, B1, Bn elements of the algebra, if the AIs are below the BIs and your symbol turns out to be positive in the I coordinate, and the opposite BIs are below AIs, and your symbol is negative in that coordinate. When you apply sigma to all of the A's, it will be below the application of sigma. So that's the notion of the algebra. And to that, we call it a partially ordered algebra. So it should be an algebra that also has an order. I'm going to be using this calligraphic notation for these pairs. And you have an algebra. This has to be a sigma preorder of A. So it has to respect all the polarities and the polarities of all the symbols. And moreover, it is going to be a partial. That's a partially ordered. And what Pigozzi did was, for those objects, for those partially ordered algebras, he created a universal algebra theory, the analogous to universal algebra. So what do we have to do? We have to start to define what is a morphism. A morphism is going to be a homomorphism of the corresponding algebras, and moreover, it has to respect the orders. It is going to be a monomorphism if it is a morphism that is moreover injective, and the image of the order should be the order of the other algebra, but it's restricted to. So you're not allowed to be. So you see, you're not allowed to order more things. So in other words, I think this other idea is better. If you can define what is the image of you have an algebra and a homomorphism, you can define what is the image. And this is going to be a monomorphism if A is isomorphic to the image by H. So it is the corresponding. This is the typical difference between an injection of a topological space into another and an embedding.
So this is like order embedding.
Yes, yeah, exactly.
Okay.
An order.
Okay.
Maybe I should have started saying that. Epimorphism is going to be morphism that is also surjective, and isomorphism is going to be epi and mono. Okay. Then what things can we prove about morphisms? We can define now what is the order kernel. The order kernel is going to be the pre-image of the order of B. Usually the kernel, the algebraic kernel, is the pre-image of the equality. Now here equality is going to be replaced with the order. So the order kernel is going to be the pre-image of the order of B. So it is all the pairs of A so that H of A is smaller than H of A. What are the properties? Well, first of all, this is actually a sigma preorder of A. And actually it is a sigma preorder of A that is larger, contains the original sigma preorder of A. So, and the kernel, the algebraic one, the kernel is the intersection of the order kernel and the reverse order. It's intersection. So these properties, as they do with the typical kernel in a universal algebra, are going to tell us how should we define the corresponding notion of congruence. A congruence, or whatever we call it, should be defined as something that satisfies those properties. Okay. So, if you have a algebra, partially ordered algebra A, we define the pre-congruences as all the sigma preorders of A that contain the order. And we call it pre-congruencies, and those are going to be the objects that are going to give us precisely this notion, the corresponding notion of a congruence for this partial. Sometimes this notation is used, but I don't think I used it in this. Sometimes just to remark that this, you see, now the alphas are a preorder, right? But I want to also consider as the analogous of a congruence. So when I am thinking about them more like a congruence, I call it alpha. But when I'm thinking of them more like a preorder, I like to use this other notation that tells me that this is an order or preorder. So, but essentially those are two notations. Okay, so properties of these precongruences of the partial order algebra. It is an algebraic lattice ordered by inclusion. The lower bound is going to be then now the preorder of A, because all the congruence or precongruences that we're considering include that one, and this is one of those. And second, of course, the upper bound is going to be the total. The total congruence, which is actually the total thing. Okay, and then here we have the typical thing. Every time that we have a precongruence, we can intersect the precongruence with the reverse of the converse, how it's called, reverse of the preorder, and this is going to be a congruence. Moreover, the quotient of alpha with respect to that congruence, it is going to be a sigma preorder of the quotient of the algebra with respect to that congruence. And then we can denote a quotient with alpha simply the quotient of A with respect to the congruence generated by the precongruence and the preorder generated. So you see, all we are doing is quotient. So indeed, those precongruences are the ones that allow us to do the corresponding quotients here. We always have an epimorphism. The order kernel of the canonical projection is the precongruence that we started with. And every time that you have a morphism and precongruence that is included in the order kernel of morphism, you have this result, which is the factor theorem. So everything is going to work. And moreover, you're going to have an isomorphism if the order kernel. So all the typical results of universal algebra are going to be satisfied here. We have a correspondence theorem. We have the notion of homomorphic image, the notion of sub-partially ordered algebra, the notion of products of algebras. All those notions are going to be satisfied. An important thing is, what is an ultra product? I didn't define what an ultra product is in the classical sense, but now this is the important one. Every time that you have a family of partially ordered algebras, you can denote, you can define the set, that set here denoted in this way. So square brackets A smaller b, that's just a symbol for that set. Is the set of all the indices so that AI is below BI in the algebra AI. And you can also define, if you have a filter F on I, you can define this relation that says the element A is below F, if and only if the set of indices that, so that A is smaller than B, so the set of indices that are the coordinates on which A is smaller than B, that set belongs to your field. This turns out to be a congruence, well, in that case, it turns out to be a precongruence, and we denote by product quotient F, the corresponding quotient. What is an ultra product? An ultra product is one quotient of those where instead of a filter, we have an ultra filter. That's an ultra product. Okay. we have also a notion of subdirectly reducible, but for the sake of time, I don't have time to, I'm going to skip it. The important thing here is then that we can also prove that if B is subdirectly reducible, if and only if the preorder of B is completely meter reducible. So it is the smallest element of your precongruence lattice is completely meter reducible. So that's what is called sometimes the lollipop theorem. Right? So you take all the precongruences that are not the smallest one, take the mean of all those, this is going to be immediately above this one. Okay. Now, and therefore, by the corresponding correspondence theorem, if you have a precongruence alpha, if A quotient alpha is subdirectly reducible, this is if and only if alpha is completely meter reducible in this because the lattice of precongruences of this one is isomorphic to the principal filter of alpha in this lattice. So and then there this is going to be completely meter reducible. So the same is going to. Okay. So everything is repeated and everything works out perfectly well. So how does the Jónsson lemma for partially ordered varieties work? Well, we have pretty much all the work done, and all we have to do is follow Bajone's proof, and everything is going to work because Picotti already proved that all the things for all the universal algebra is ready to be used for these partially ordered algebras. So first of all, let's recall what is this lemma 5. Let's call it now lemma 5 prime. If you have a partially ordered algebra, you take a set B of precongruence, that this is a typo, it should be a set of precongruences, and you take an ultra filter over B, then the quotient of A with respect to the Bajone's element, xu, this is going to be isomorphic to a subalgebra of an ultra product of all the quotients. The proof is pretty much identical, but there is just a little difference because now we don't have equalizers, we have these inequalizers. What do we mean? Again, we form our diagram, our partially ordered algebra, the map that sends this to the product of all the possible quotients with alpha and b, and the canonical projection into U. And this is F. And now here consider the canonical projection into X, AX. Now, F of A is going to be FA, FB belongs to the precongruence determined by the ultrafilter, if and only if the inequalizer of the image of A and B by nu, this belongs to that's the definition of that congruence. And what this means is that, what is the set? The set is all the elements of B, all the coordinates in which A and B are ordered according to the that precongruence alpha. And this means that those are going to be all the elements of B, so that the principal, so that the precongruence of AB is included in alpha. And as before, this is the set of all the elements of B that are above the precongruence determined by A and B. And yeah, we follow Bajone's proof, and it's exactly the same. And finally, what this means that this precongruence is inside XU. What it means is that A precongruence class A is below the class of B. So belong actually to this. Therefore, is that this is the ordered kernel of that, and therefore we have an isomorphism. So that's the first part, and the second part is just Jonsson's lemma. Again, you have a class of algebras, and those are partially ordered algebras, so that this is precongruence distributive. Now, we need that the lattice of precongruences is distributive. Now, the subtheoretically reducibles belong to this class, HSPU of K. And the proof follows very much the same argument as before. If you take your partially ordered algebra, take your set B of all the precongruences so that a quotient belongs there. You take an ultrafilter, an arbitrary ultrafilter over B, then you can prove that XU belongs to this precongruence by the previous level. So this belongs to ISPU of all these algebras. All those algebras by our choice belong to ISPU, so you have ISPU of K, which is ISP. Therefore, this means that for every ultrafilter, this element already is in B, so B is equal to B prime. This means that this is compact, and therefore, and that's the first part. The second part is, okay, if you have a precongruence so that this is reducible, then that element there will be completely reducible. In particular, it's going to be reducible. And because we are assuming that the lattice of precongruence is a distributive, then this is going to be mid prime. And mid prime is characterized, as we said before, by compact elements, by compact sets. And now the intersection of all degrees will be not the equality, but it's going to be the inequality. It's going to be the order. And this is included in every precongruence, in particular in this one. Therefore, this means that there is one in B, one precongruence in B that is below sigma. So the A quotient psi can also be expressed in this other way. And this is a homomorphic image of an ISP, which is an ISP. Okay, now, couple of things, couple of remarks to finish. I see that I am already over my time. Here I am claiming that ISPU is equal to ISPU. I don't have a proof of this. Why do I believe that is true? I believe this is true because all the theory really it runs in parallel to the theory of to the classical universal theory. And how do you prove it in the universal algebra, classical universal algebra? What you prove is that usually, this is what you do. You prove that ISPU is an operator that is going to give you all the algebras that satisfy all the universal forms. So if you take that twice, okay, if you're already taking all the algebras that satisfy all the universal formulas, if you take it twice, you are not growing your set, your class. I believe that this is true. It has to be proven. Another thing that, yes. And the other thing, just to answer Alex's question at the beginning, is what happens? You start with a class of algebras, you generate your variety, in that case, your variety of partially ordered algebras. How do you know whether this is absolutely reducible or not? Well, in classical universal algebra, what you do is you prove that this class of algebras has Mal'Sef terms. Mal'Sef terms are particular kind of terms that for every algebra of your variety, when you apply those terms in some specific elements, in some specific ways, some equations become true.
Massive terms?
Mal'Sef.
Mal'Sef. CEF.
Yeah.
Mal'Sef. Thank you.
Finding Mal'Sef terms for in this theory of partially ordered algebras turns out to be very, very difficult. I couldn't prove it. I couldn't prove that those terms should exist. in classical universal algebra, it is very nice because if your algebras, your class of algebras turn out to be orderable in some way, if you have a lattice that is definable by some terms, then you can prove that you have massive terms, and therefore your variety is congruence distributive. So most of the classes that we usually use in algebraic logic to give semantics to our logics are congruence distributive because they are orderable, and the order can be defined using terms of your language. But we lack this here, so we would like to. And my final remark is that at the end of his paper, Bajone says that this theory can be also used very easily to prove the generalization of varieties to quasi-varieties that Vygotsky proved. So Vygotsky proved a generalization of Johnson's lemma for quasi-varieties. Bajone says without any proof, all these also can be used for quasi-varieties. So I believe that if this
So
is
quasi-varieties in the ordered sense.
In the non-order.
no, in the non-order sense. So I believe that if he's right that it can be used, then I think that it can also be used. But I don't have a proof of that. Okay,
Very
that's all.
nice.
Sorry that I didn't go with time.
Sorry. No problem. Thanks. Maybe a quick question, or if I had a question about lemma 5 there. Does it use any distributivity in lemma 5?
Lemma 5?
Yeah, this in the last panel, first lemma. It was
Yes.
5 from
5 prime, yeah. There's no distributivity.
There is no distributivity here now.
Insisting. Okay.
The distributivity only appears in this part, and it is when you take a precongruence so that this is directly reducible. This being directly reducible means that the congruence or the precongruence that you chose is completely meter reducible.
Yes.
That is where distributivity happens.
Nice.
And that is important because in that case you will have a means prime, and you're using then that this is compact. That's how everything is.
So for compactness, you use the less or equal formulation. But for this to work, you also need the equal formulation. And then is that the reason where distributivity comes in? Because that's what makes these two formulations of varieties the same.
So actually the lattice theoretical part is independent. It works already there. If your thing is distributed, it's going to be the distributivity is to exactly to indicate that if you have a compact and you have this is above the intersection of a compact, then it is going to go above some of them, but we know that this is meter prime, not meter reducible. Distributivity is used to translate or to equate meter prime and meter.
So could there be something weaker than distributivity, which gives you the equality between meter reducible and meter prime?
I don't think so, but I don't know.
Why is this equivalent to distributivity?
I think they're
I want to say yes, but I don't have a proof in my head. So
Maybe
don't
it's
take my
equivalent,
word.
right? Because if not, there could be a potential generalization. Maybe.
I know that there are some generalizations in which you don't have distributivity, but you have modularity.
So is there a Jónsson lemma for modular?
Certain
Modular.
certain congruence modular. Not all right.
Never heard about congruent modular, right?
Oops.
Oh. Oh, this is where there's Hölder theorem. Right.
The original one-set condition.
Right.
Okay, I'm going to stop the recording and
Thank you.
thank the speaker again.